Hey nerds! AI is everywhere. Every company seems to be talking about it, and it seems like every product suddenly has AI built into it as well. And there are headlines pretty much every day that are making it sound like we're right on the edge of some sort of major event. Something crazy is about to happen. Now, depending on who's talking, that event is either going to solve all of science. It's going to create this utopia where none of us are ever going to have to work anymore. Or the alternative is it's going to become sentient and end humanity.
We have only bits and pieces of information, but what we know for certain is that at some point in the early 21st century, all of mankind was united in celebration. We marveled at our own magnificence as we gave birth to AI.
The problem, from my perspective anyway, is that all of this news that we're bombarded with, first of all, it's just hype. So much of what we see online is hype. But the main issue is that it's being made to seem like there is this one singular thing that will solve everything, like AI, ChatGPT. If you know, you know. Okay, stop. Okay, the truth here though is that when people say AI, they're not actually really talking about the same thing. The same word is being used to describe things like ChatGPT writing essays, and then image generators producing artwork, recommendation systems deciding what you watch, as well as medical systems detecting patterns in scans, and models that can predict the structure of proteins. But because we group all of them together under this same label, it creates this impression that they're just all part of this single idea. That there's one kind of a system and it's gradually improving across everything, getting better at language and then images and then science. And it's reinforcing this idea that all of this is moving towards something like general intelligence. But that's not what's happening. So today I'm going to do my best to break down what AI is, how it's being used right now, and what that means for all of the products on the market. This is an AI reality check. So the term AI isn't referring to one specific method or one specific technology. It's a broad label that gets applied whenever a computer is doing something that we would normally associate with human intelligence. But recognizing a face and writing an essay are fundamentally different tasks. Now that's the same with predicting protein structures and then driving a car. What you end up with are systems that become very good at one specific task, but they don't gain any broader understanding of anything outside of that one task. So most AI systems are specialized tools. So when one of these areas improves really quickly, like language models have over the last few years, the media creates this kind of impression that AI as a whole is suddenly advancing, and that we're all moving closer to something general. But the jumps that we see, well, they're local. They're not global. Most frustratingly about all of this hype that we see online is the idea that it's all so sudden. But AI isn't new. What is new with AI is how visible it's become. But it's not the work itself that's new, because people have been trying to build systems that replicate aspects of human thinking for a long time, and they've approached it in very different ways depending on what they thought intelligence actually meant. Now we can go all the way back and we can see the roots of this in philosophy. A lot of physics is rooted in philosophy. Aristotle was trying to formalize reasoning, to describe how you can take statements and then reliably arrive at conclusions. Now a simple example is a syllogism. So all swans are birds, some swans are white, therefore some birds are white. What matters there isn't the content of the sentences, it's the structure. The same logical form works regardless of what the words are. Now, this suggests that reasoning might be something that you can separate from meaning and then turn it into a process. So that idea then carries forward into mathematics and logic and eventually into computing. So by the time we get to Alan Turing in the 1930s and the 40s, the question becomes, what can a machine actually do? So Turing introduced the concept of a theoretical machine. It's now called the Turing machine. This is a machine that follows a set of rules to read and write symbols step by step. So any computation that can be defined algorithmically can, in principle, be carried out by a machine. That's the foundation of modern computing. But then, in the 1950s, Turing asked, can machines think? Now, instead of trying to define what thinking is, he reframed the problem into something that's more observable for us. So if a machine can carry on a conversation that is indistinguishable from a human, should we treat that as intelligence? Then in 1956, at the Dartmouth conference, the field of artificial intelligence was formally established. Now, the goal laid out there was extremely ambitious. They wanted to build machines that can use language, form concepts, solve problems, and improve themselves. The assumption was that these abilities could be described precisely enough that a machine could simulate them completely. Everybody's busy. Can't wait for the night to begin. So early AI research focused on that idea. Systems were built around rules and symbols instead of learning from data. They manipulated representations of knowledge according to predefined logic. Now, in controlled environments, this worked really well. Programs could solve logic problems, they could prove mathematical theorems, and they could play structured games. But when you move outside of those controlled settings into like real world tasks, things like language, perception, or recognizing objects, you don't have clean, complete sets of rules. Things get complicated, they get really messy. So it became clear to the researchers that intelligence isn't just one thing that you can write down as a system of rules. It's a collection of different abilities, perception, language, memory, reasoning, decision-making, and most importantly, they don't all work in the same way. So instead of one unified path towards building a generally intelligent machine, the field had to section itself. Different groups began working on different pieces of the problem. Speech recognition was one, computer vision was one, game playing was one, language processing, and on and on and on. And that is still how AI is used and developed today. It's why we have systems that are incredibly good at very specific tasks. Modern AI builds systems that capture small parts of intelligence. So these early attempts at AI were about writing down rules, like trying to describe exactly how to solve a problem step by step. Now, instead of telling the system like what the rules are, you give it examples and you let it adjust itself. This is machine learning. The system takes the input, it produces an output, and then you compare that to what you wanted it to do. If it's wrong, you adjust it slightly, and then you do it again. And again, and again, and again, and again, and again, across large amounts of data. So a really good example of this is something like spam filtering. So you take a huge number of emails, label them as spam or not spam, and then the system starts picking up on patterns. It might notice certain words and structures or certain combinations of features. Now, at the beginning, it's basically guessing. But each time it gets something wrong, you like nudge it in the right direction by moving something to spam or back to inbox. And over time, we then eventually just ended up with mailboxes where we didn't have to mark things as spam anymore. We suddenly just had a spam inbox. That's where it all went. That's what learning means here. You see, it's not understanding in like the way that we normally use that word. It's just that the system is getting better at producing the correct output for a given input by reducing its errors over time. Now that's fine for very simple problems like your inbox. To do a much harder task though, You need something that can deal with more complicated structures in your data. And that's where neural networks come in. So a neural network then, it's just a function with like a lot of adjustable parameters. The input goes in, it passes through a series of layers, and an output comes out at the other end. Now, each layer applies a transformation to the data and passes it forward. What that actually means is that it basically takes a bunch of inputs, it weighs them all differently, combines them, and then slightly reshapes the result before passing it on to the next layer. Now, on their own, each of these steps are really simple, but when you stack enough of them together, the system can represent very complicated relationships. So in something like image recognition, the earlier layers, they'll tend to pick up very basic features like the edges of things and simple patterns. The next layers will combine those into more structured features. And then the later layers will combine those into things that correspond to parts of objects, eventually whole objects. The main point here is that in this process, none of that is explicitly programmed. You don't tell the system what a cat is or define the features ahead of time. You initialize the network, you run data through it, you basically show it pictures of cats and birds and dogs, and then you compare the output to the correct answer and adjust the parameters throughout the network so that it improves over time. Mathematically, what you're doing is you're defining some measure of error. It's called a loss function, and then you're adjusting all of those parameters in a way that reduces that error. So for modern systems, there can be millions or billions of these parameters. Each one is just a number, but together they define a mapping from input to output that gets shaped during training. Once you've established neural networks, the next step is deep learning, which is just neural networks with many, many, many layers. More layers means more depth, which lets the system build up more complicated relationships, which is why these models work well for things like vision and speech and languages. Different models all follow these same general ideas, like the machine learning, neural networks, deep learning. But the structure of the problem is going to be different for each model. So that's a simplified version, but that is basically the basis of AI, and it's not that complicated. It's been around for 70 years. So what's happened in the last few years to cause all of the hype? So AI models have been used in computer science and scientific research for decades now, but there haven't been that many products on the market. Most of our experience, without even realizing it, was things like predictive text, recommendation videos, ranking search results, things like that. But a few years ago, when OpenAI released their first model of ChatGPT, it looked to the world like there was some major breakthrough that came out of nowhere. But really, it was a combination of things that have been improving for a long time and then all put together to make a product. It comes down to data, compute, model development, and the interface. Let's start with data. Machine learning systems improve by seeing examples, and for a very long time that was a big limitation. So you might have a model that works in principle, but if you only have a very small data set, it can only learn something very narrow. If you want an algorithm to learn the right outcome, you need hundreds of thousands of data points. If anyone ever tells you that they trained a model on a few hundred data points, walk away. Just walk away. Historically, there's only a few places that you could get that amount of data. One of the most famous ones is CERN. They have been using machine learning for decades. So what changed for the rest of us? More recently, it was the availability of all of this large-scale data in the form of text, images, and audio. And where did they get it all, you guys? They scraped the internet.
Ladies and gentlemen, I'd like to present to you the internet. Oh, please, no flash photography, you'll harm the internet.
Suddenly, these developers had access to massive amounts of written language, labeled images, code, all sorts of unstructured and structured data that gives these systems something to learn from at a scale that just wasn't possible before. And we gave it all to them for free. Then we have compute. Training these models is not just about running the data through once. You have to repeatedly adjust large numbers of parameters over and over and over again, trying to reduce these errors across the entire dataset. Now, for modern systems, that means dealing with millions or billions of parameters and running huge numbers of calculations. That only becomes practical with specialized hardware, particularly GPUs. These are really good at handling large numbers of operations in parallel. Without that, even if you had the right model and you had the right data, you wouldn't be able to train it in any reasonable amount of time. Then we have the models themselves. Now, like we said, neural networks existed long before this current wave of AI, but they didn't scale well for certain types of problems, especially things like language. You see, earlier approaches struggled to keep track of long-range relationships in text. So basically things like context across a sentence or across a paragraph. That changed with the introduction of transformer models. So instead of processing text step by step, they allow the system to consider all parts of the input at once and then decide which parts are more relevant to each other. That makes it much easier to handle longer, more complex sequences of language in a coherent way. Basically, before they would just go like word, next word, or like character, next character, next character. Now they can kind of go like, oh, this is a sentence and this part of the sentence is more important than this part of the sentence. So this is what the next bit should be because I have a memory of what that part of the sentence was, if that makes sense. And then we have the interface. See, a lot of these systems existed in research contexts before they became available to us. So what changed is that they were turned into products, ones that people could actually interact with directly. Now, this happens with most scientific research. It exists for decades in the research space, and then a company comes along, takes that research, develops it into a product that can be sold to the public. So a conversational interface makes a really big difference for the most of us. Like, instead of writing our own code or having to work with a specialized tool, we can just like type a question and get a response. And that's what makes something like ChatGPT feel different from the earlier systems that were around, because it's not just about what it can do, it's about how accessible it is. So putting all of this together, the large data sets, the sufficient compute power, the effective model architectures, and these interfaces that people can actually use, creates the impression of this like sudden jump. But the jump is that they became a commercial product. Now, at the moment, AI is being used as if it refers to a single system that's steadily improving over time, bringing us towards something spectacular or disastrous. ChatGPT is in the news, then image generators like Sora, and then something like AlphaFold, and it comes across as if we're seeing different versions of the same technology being applied to different areas. Like there's one core intelligence underneath it all, gradually getting more and more capable. What actually exists is a collection of different approaches built around different kinds of problems using different types of data and often behaving in very different ways once you look under the surface. So let's look at a few of the well-known systems and talk about what they were actually doing. We're going way back. We're starting with the OG, chess. Back in 1997, IBM's DeepBlue officially defeated chess champion Garry Kasparov. Now, chess is a closed system. The rules are fixed, the board is fully observable, and every move leads to a well-defined next state. There's no missing information here. There's no ambiguity about what's happening. That makes it possible to treat the game as a search problem. So DeepBlue worked by exploring a very large number of possible move sequences and evaluating them using functions designed by humans. Now, those evaluation functions encode things like the value of the pieces, board control, advantages of different positions. The system doesn't need to understand chess. It just needs to assign scores to positions and search efficiently through possible futures. You can represent the entire game state in a clean, structured way, and you can calculate what happens next without uncertainty. So given enough computing power, DeepBlue can just look further ahead than a human can. Now, let's compare that to Go. Because in 2015, Google DeepMind's AlphaGo defeated the European champion Fan Hui. Another board game with 2 players, but this time the number of possible board positions is a hell of a lot more. You can't just search through them in the same way because the branching factor is just way too high. The number of possible futures grows just too quickly. So instead of trying to evaluate everything directly, AlphaGo uses neural networks to estimate which positions are likely to be good and which moves are worth considering. Those networks are trained on human games, and then it's reinforced through self-play, where the system plays against copies of itself millions of times. So instead of this exhaustive search over all the possibilities like DeepBlue, you get a guided search where the model narrows down the possibilities to a manageable subset and then focuses the computational effort on those possibilities. Now, this is a totally different system, not just in how it's implemented, but in how it's arriving at its decision. It's not calculating everything, it's just learning patterns that let it ignore most of the search space. So let's move on to protein folding. This is the big one that everyone keeps throwing out as the game changer. This is the evidence that people are using that AI will revolutionize everything. AlphaFold. It's another model by Google DeepMind. Now, AlphaFold 1 came out in 2018, with the current version, AlphaFold 3, announced in 2024. And again, this is an entirely different type of model. The problem here is to predict how a chain of amino acids will fold into a 3-dimensional structure based on physical and chemical constraints. The space of possible configurations is enormous, and just like a brute force search is just completely impractical to do. So what AlphaFold does is it learns relationships between different sequences and structures from large data sets of known proteins. And then it uses that to predict what the most likely structure for a new sequence is. An important detail here is that the model is built around the structure of the problem itself. It incorporates geometric relationships, spatial reasoning. It has domain-specific constraints. It's not just a generic AI system pointed at biology. It's a model specifically designed for that particular type of data and that particular kind of prediction. It's incredible. It speeds things up significantly, but it's designed to do it, specifically that problem. And then we have generative models. These are the AI models that we're using. Here, the problem is completely different again, surprise, surprise. So you're not dealing with fixed rules here, or we're not dealing with physical constraints like AlphaFold. If we look at a language model, right, you're dealing with sequences of text where meaning is distributed across context and where the same idea can be expressed in many different forms. So a language model is trained to predict the next token in a sequence. Now, when you scale it up in terms of data, model size, training time, it can capture really detailed statistical structure in language. It learns which words tend to follow others and how sentences are structured and how arguments can be built. It can learn how different topics can be discussed in different ways. So when you ask it a question, it's not retrieving an answer. Like, it doesn't have a database and it just goes and looks for the correct answer. It's generating a response that fits the patterns it has learned from training data. That's why it can write, explain, summarize, and translate things, but it's also why it can produce something that sounds completely convincing and still be entirely wrong, because the system isn't checking its output against the real world or a correct answer. So if a model is trained on biased data, it will reproduce those biases. This is completely logical, right? I was trying to think about a way to explain this or express this, and I was think about it this way, right? Say you got every single review ever written about every sci-fi movie, but for 2001: A Space Odyssey, you only include negative reviews. No positive ones, like, at all anywhere. Then you ask that model to write you a list of the best sci-fi movies ever made. Will 2001 be on it? No, of course it won't be. And if you ask it to write a review of the movie, it will write a bad review. What if you ask it to then write a review on a documentary? Well, it's been trained specifically on science fiction, so that's also going to be a bad review. It's not going to understand what a documentary is versus science fiction. So now think about this for data that contains homophobia, racism, misogyny. The model can't make its own decisions based on social cues and life experience. It will only reflect what is in the data that it was trained on.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
So when all of these systems get grouped together under the heading of AI, what gets lost is the fact that they are solving different classes of problems. Now, they do use overlapping ideas, of course, like optimization, learning from data, large numbers of parameters, but that doesn't make them interchangeable in any way. But when we see people talking about it online, it's presented as if a breakthrough in language models is like a step towards solving scientific research in general, and it's seen as evidence that AI is becoming broadly intelligent. But the systems don't transfer in that way. If you take a language model and give it a protein folding problem, it won't suddenly become AlphaFold. There is a difference between something that works well in a controlled setting and something that's turned into a product that millions of people can use. Now, in research, we will define a problem clearly. We'll collect data, we'll curate the data set that represents the problem, and then we will build a system that performs as well as possible on that task. We can control the inputs, we can evaluate the outputs carefully, and we can measure performance in a meaningful way. That's the environment where you get systems like AlphaFold or models used in physics and astronomy. They're not designed to be flexible. They are designed to be precise. And we've been working on those models for decades. Building an AI product for the market is an entirely different goal. The reality here is that most people aren't really reacting to what these systems actually are. They're reacting to what they think these systems are about to become. Artificial General Intelligence, or AGI. And then if you go a step further, things like the Singularity. Now, AGI is not a chatbot that's really good at writing or something like AlphaFold solving a specific scientific problem. The concept of AGI is a system that can operate across different kinds of tasks, learn new things quickly, adapt to new situations, and then apply knowledge in like a flexible way. Something that isn't limited to one space, but can move between them in a way that looks more like how people think. But even the systems we currently have that may feel to you like they're more general, like language models, they are still confined within a very specific framework. They take in text, and they generate text based on patterns that they've learned. Now, they can be used for lots of different tasks, but that flexibility comes from the structure of language, not from a general intelligence or a general understanding of the world. They're not building up knowledge over time in the way that a person would. They don't have a consistent internal model of how the world works, like goals or intentions or any sense of like what actually matters to humanity or the world. There's no way to transfer what they've learned in one area into another area in any reliable way. So this idea that what we have now is just like an early version of AGI, or that we're just a few iterations away from it, has nothing to do with how these systems really work. What we've actually seen over the last few years is that if you take this same basic approach, train on more data, use more compute, make models larger, you'll get better performance. Absolutely, especially when it comes to language. We've gotten better at modeling patterns in data. As a result, you get more coherent outputs, which makes you feel like the systems are becoming more capable when you interact with them. But language models in particular are very good at creating that impression. You can ask them questions across lots of different topics, and they'll give you answers that sound reasonable. They can explain things, they can summarize things, they can write us code, and they can hold conversations. They pass the Turing test. So it feels like there's something general happening there. But if you look at how those outputs are being generated, it is still the same process. Now, if we're nowhere near a general intelligence, then we are definitely not heading towards a singularity anytime soon.
I had strings, but now I'm free.
This is the claim that once systems reach a certain level of intelligence, they'll be able to improve themselves, which then leads to this rapid increase in capability that we can't predict or control. But for that to happen, we need a few other things to be true here. We need systems that can redesign themselves in a meaningful way. We need them to be able to improve their own learning process, not just like apply it. And we need that improvement to like compound really quickly. Like at the moment, none of that is how current systems work. They don't train themselves. They don't decide what to optimize for. They don't go off and redesign their own architecture. All of that still requires human input. It needs infrastructure. It needs a lot of iterations. So if we go back to the start, what AI isn't really all that complicated. But the media and the grifters online are using one word to describe a lot of very different things so that everything starts to blur together. ChatGPT, image generators, systems used in science, recommendation algorithms, they all sound like one same system that's getting better. When really, they're all different systems that you can't just combine to make a super AI that's good at everything. Look, it's not that these ideas are impossible. It's not that we're not heading towards AGI, or it's not that a technological singularity isn't on the distant horizon. It's just that they don't follow directly from what we currently have. Right now, we're getting better at building systems that are very good at specific tasks, and we're integrating them into tools and workflows. We're using them to process large amounts of data, to automate parts of jobs, and generate content at scale, which can be very useful in specific contexts when used responsibly. The current problem and the current fears that people have about this march towards AGI is that the models that we currently have are not always being used responsibly. And we're not sure if this is actually going to truly benefit us on the scale that the companies selling the products want us to believe. Recommendation systems can shape what people see and engage with. This makes it harder to get your work seen. Automated systems can affect things like hiring or lending. So obviously biases in the data that it's trained on is going to be a major issue. Generative models are producing large volumes of content very quickly, including misinformation, creating AI influencers, and making it really hard to find accurate information online. This is obviously my biggest concern right now. Now, there are a huge amount of other topics around AI. We've got like water usage, data centers in space. Be a video on that, should be up already. What it means for us in terms of the environment, and whether we're heading for a utopia or a dystopia. I know which one I'm betting on. If you would like me to break down a specific topic related to this, I am very happy to look into it and make a shorter video. So do let me know in the comments what you want to know more about. But for today, I just wanted to clear up some of the blurriness that even I feel when I see all of this AI chat. We talk so much about how it's revolutionary without really explaining what it actually is. And in this day and age, we are surrounded by technology. We are so dependent on it. And that's why I do these monthly deep dives, whether it's about something real or whether it's like something in fiction. I just want to help you break into understanding the science behind it all, because it's important that we all do understand what we're buying into. This is also why I've started an everyday science playlist where I'll post some shorter videos explaining what actual technology that we use and hopefully help you see where research comes into it. When a new product comes out, it usually means that there was decades of scientific research happening all over the world to explain how something works, so that someone else could then come along and turn it into something that we all use in our everyday lives. AI is a great example of that. 70 years of research and development eventually brought you the TikTok algorithm, ChatGPT, and AlphaFold. But be careful of the hype, because once it's a product, the story isn't really about the science anymore and what it can be used for. It's about who they can sell it to, and we are all a target. Stay safe out there and stay nerdy.
Do you use AI? Absolutely. Do you use ChatGPT? Do you love ChatGPT? I love ChatGPT. I love it.